Hello and welcome back to what has become quite the epic journey in my fix-up of a 1950s console entertainment system. Almost everything you could think of, lots of taking apart, and cleaning, and putting back together, a little carpentry, some hazmat mitigation, a little mechanical work, proving a cognitive bias effect, but in the end I finally did make a little progress.
We have life!
And of course in episode 6 I left you with a little cliffhanger. Why no valve number 3? The answer to the cliffhanger from part 6 is quite simple. In troubleshooting, it's always best practice to isolate as much of the circuit as you can, and thus narrow down your search for any fault. Therefore, by taking out valve 3 and keeping the console in phono mode, I isolated the audio section from both the AC heater circuit for valve 3 and cut it off from any output from the other two boards. In hindsight, I really should have hooked up a signal generator to get a little more than just hum out of the audio section, but at least I know it works now.
We have life!
The title of this video also had an asterisk, which indicated this footnote, applying what I have learned. Now I initially thought I would blow the heater up V3 from the 120 volts AC, so to prevent that I just took it out, but I was dead wrong. Now for those of you who don't like boring circuit reviews, you can skip ahead a little bit. The circuit starts with our AC input, next a 510 10-watt dropping resistor, next a 19-volt 100 milliamp lamp in parallel with an NTC resistor, then another one of those, the heater of valve 3 is next, and finally a connection back to ground. So a simple enough series filament circuit. But I didn't know what the NTC resistors did in the circuit. Well, first let's see what an NTC resistor is. Now I'm going to ignore the pages of math that usually come with this sort of explanation and keep it very simple. We'll just start with a simple XY graph, and on the x-axis we'll add resistance increasing, and on the y-axis temperature increasing. Now if I was to start increasing the temperature of the resistor, and at the same time record the resistance of the resistor, I would start to see a graph like this. A simple curve where the resistance goes down as the temperature increases. In this case, we started at 1000 ohms and ended up at 300 at some working temperature. Now, I didn't take the time to make a graph for the resistors in this circuit, but I did take the cold resistance, and it was about 320 ohms, and I also tested them when they were hot, and it was about 220 ohms. The question is, why even have them here? Normally, you just have one in series, as we see here in the other heater circuit. Now their purpose is to stop this. Now this is called heater flash, or at least that's what I've been told it's called. And it's caused by the inrush current when the device is turned on. And it can burn out a heater and definitely cuts the life of a heater over time. So the NTC resistor limits this inrush current because it presents a high resistance when cold until it heats up and maintains its working resistance. Like I said earlier, an NTC resistor in series makes perfect sense, but here we have one in parallel with an incandescent bulb. Now this lamp, like any other incandescent bulb, will act like a current limiter, and in this radio we have two in series, so the current will never really rise that high. Now the NTC resistor, because it's in parallel, really does not have much effect on the circuit. It drops the overall resistance of the lamp from about 10 ohms down to about 9.5. Now to understand how the NTC resistors fit into this circuit, we have to do just a little bit of math, so bear with me. Now to start off, we have to figure out what the voltage drop is across our big dropping resistor, and we'll label that V1. Now we know that the nominal input voltage is 117 volts, which was the Canadian standard at the time. The voltage drop of V3's heater is 26 volts. Initially I thought it was 19 volts. Because the name of the valve on the schematic is 19AQ8, and in the North American naming system, the first number on a valve's name is its heater voltage. Digging a little deeper into tube lore, I discovered that this valve is also called the 20AQ8, the 26AQ8, and even the 25AQ8. So I went back to the European designation, UCC85. Now, contrary to what you might find on the interweave, the U does not stand for universal. It just means that the heater of the valve is rated at 0.1 of an amp. Going back to the data sheet, we can see that the voltage rating for the heater is 26 volts. Though it does say in other places in the data sheet that it can run from anywhere from 20 to 26 volts, as long as the current is 100 milliamps. Now we know from before the voltage drop of one of our lamps is 19 volts, so we can add both of those in. Now we just have to solve for V1. Now V1 is figured out with this formula. The voltage total minus the sum of all the voltage drops. Stubbing in our values, we get 117 minus 26 plus 19 plus 19, or 117 minus 64, which will give us a value of V1 of 53. Now we can figure out from this the value of resistor we need at V1 by simply applying Ohm's law. Resistance is equal to voltage divided by current. So 53 is our voltage drop, and 100 milliamps is our current, so the dropping resistor should be 530 ohms. So the 510 ohm resistor in the circuit will do us just fine. We can also figure out what the wattage of the resistor needs to be. Again, using Ohm's law, it's simply the square of the current times the voltage. And that gives us 0.1 times 0.1 times 530, and that comes out as 5.3 watts. So the beefy 10 watt resistor that's in the radio is fine for us. Now suppose what happens if one of the lamps was to burn out. Now our circuit consists of two resistors, a lamp and resistor in parallel, and then the heater of our V3. Now we have to solve for V3, which is the combined voltage drop of R1 and R2. 117 minus 45. And now we have a voltage drop of 72 volts. And the combined resistance of R2 and R1, again, is just 72 volts divided by 0.1 of an amp, which gives us a total resistance of 720 ohms. Now we can figure what the resistance of R2 is, which is simply the value of the total resistance minus the value of resistor R1. So 720 minus 510, which is the resistor in our circuit, which gives us a value of 210 ohms, which matches very closely to the values I took for those NTC resistors. So that's why you see these NTC resistors in parallel. If they weren't there, losing one bulb would mean the radio just wouldn't work. As well, because they're NTC resistors, they're now going to start doing their job and limit the inrush current, thus saving the heater of valve 3. You really have to admire the valve designers and engineers back in the day. Selecting a valve with a heater current of 0.1 of an amp really simplifies the arithmetic for the design. And given that there are well over 200 tubes with the U designation, it must have been very popular at the time. Unfortunately, that doesn't help me with today's problem. 2 new lamps is going to cost more than a full set of tubes. One is even more than I paid for the whole thing. Now I could just leave the bulbs out, as it will work perfectly fine without them. But I'd like to see this system be as close to original as possible. I did try and source an alternative lamp, but the big problem was trying to find one that worked with an amperage of 100 milliamps. So I decided to try this. So we start with our circuit without the lamps. Now you can replace any bulb with an LED, you just have to take things into consideration. First we'll need a nice big dropping resistor, and because our voltage is alternating current, we need to put a diode going in the opposite direction of the LED. And I just dropped this circuit in the same spot the lamps were, and Bob's your uncle. Here's the end result of my little proto boards. I have a diode, an LED go in the opposite direction of the diode, and a big ass resistor there, 10 watt at 1K. To figure out what resistor I needed, I simply swapped out higher and higher. Started with 100K and morphed all the way down to 1K. With 1K I got the right balance of power through my system. So they got about 20, anything under 20 volts here, 24 volts. In the old system with the incandescent bulbs, they acted sort of like an inline current limiter, each sucking up 24 volts, about I think it's 19 volts they each suck up at very low wattage. And then these big ass resistors here, this big ass resistor and that resistor do a thing. So now all I got to do is hook that up here and that there, turn on my power,
There. Everything switched in. Turn her on. There. We have two LEDs glowing very brightly. And if I check my AC voltage across here, I get about 23 volts, and then across here I get about 22 volts, which is just what I need. And that's about it, really. Now I can go and I'm gonna, well, you can hear it humming there, so I'll turn it off. And what the voltage is once it warms up. 22, that's still fine. That can go all the way up to 25. So I'm not much worried about that. So I got all my tubes finally working. So now I'm gonna go, and while I got it in this configuration, I'm gonna go see if I can get some alignment out of it. Just gotta set that up next. So this is the IF transformer I have to adjust to do an alignment on it for AM. And if you notice, there's no pins to go in. What happened, I so much as touched them and they went in. There's no way I could get them out. And I've looked at the other ones. This is the same style, and it's basically just puttied or glued in place. I'm going to take that out. See what's going on the inside of that. What fun. It's one thing after another.
Oh well, a few more episodes to go, I guess. So stick around for the next episode where I might get those cans fixed.
I hit it! I hit it!
My cans! My precious antique cans! Oh, look what you done to them.